All right, welcome back to Real Analysis. We're going to continue our work in chapter 4 here, looking at the nature of sets and points in the real number line. Last time we were looking at the so-called topology of the real number line, that is the kind of nature of open and closed sets. One of the main facts in that lecture was that a set is open if and only if its complement is closed. And then we ended the lecture by introducing this notion of locally bounded functions. So we're going to start this lecture, section 4.5. And actually section 4.5 has many subsections. So this is kind of the intro to it, and then mainly the material that's in section 4.5.1. I'll just add that to help your reading line up with what I'm talking about here. So let me remind you that a function, say from the real numbers to the real numbers, is called locally bounded on some subset of the real numbers if it's bounded at every x in that subset. That is, for every x, there are two numbers, epsilon of x and m sub x. They're positive. And the function's value never exceed m sub x on that epsilon sub x neighborhood of x. All right, so every point is contained in a neighborhood on which the function is bounded. It's called locally bounded. And the kind of fundamental question that's driving the material in this subsection is the following. If you take some locally bounded function on a set, is it necessarily bounded on that set? Because here the bound, the m sub x, if you like, well, the notation indicates this, it depends on m. So if I'm asking if there's some global bound, I'm wondering, well, is there some m that works for all x's in E, all right? So is there some one number m that's greater than 0 such that f of y would be less than or equal to m for all y in E? All right, let's look at some examples. First example, I'm going to take the subset E to be the unit interval, open unit interval, and just take the reciprocal function, f of x equals 1 over x. I've drawn what I think is a familiar graph. And I claim that this function is locally bounded on that interval. Why is that? Well, because if you pick an x, I've drawn one here, and you say let epsilon sub x be half x, so I've drawn the little epsilon neighborhood in red down there. Well, then any y in there satisfies these inequalities. Stop the video and check it. I'm not going to kind of walk you through all the arithmetic of this thing. But that would be equivalent to y being between x over 2 and 3x over 2, right? So the absolute value of f of y, which is just 1 over y, you can drop the absolute values because y is a positive number, it would be no more than 2 over x. So I can take that to be my m of x. It depends on x, of course. The smaller you take x, the bigger m sub x is going to be. But locally on that little interval, this little epsilon neighborhood of x, our function is bounded by 2 over x. So it's locally bounded. But the function's not globally bounded on 0, 1. You can look at the graph if you just want to kind of go with that kind of calculus version of it. But if you want to be a little bit more precise, if you give me some number m that's positive, well, then 1 over 2 times it is an element of the unit interval. 1 over 2 times m is a positive number. I suppose I should say something about why 1 over 2m is less than 1. I mean, it wouldn't be true for all m, but for large m, 1 over 2m is less than 1. And then f of it is 2 times m is bigger than m, right? So I've got a locally bounded function that's not bounded. So the answer to the question above is no. If a function is locally bounded on a set, is it necessarily bounded on that set? No, it's not. As we'll see below, one of the reasons that this can be happening here is that this function, or excuse me, this domain is not a closed set. It's got a accumulation point, x equals 0, that's not in it. And that's pretty much responsible for the fact that this example can happen. Okay. Let's look at one more example. I'm going to leave most of the details here to you. If you take the function on the interval from 0 to infinity, that is a closed set. The interval from 0 to infinity, including 0, is closed. Its complement is the open interval from minus infinity to 0, which is an open set. So this complement set is closed. And take the identity function on it. That's locally bounded. I'm going to leave the details to you. I would recommend you stop the video and kind of work it out. It's not going to be too tough, but it's good to practice the definition. But it's certainly not bounded. It's not bounded because, well, the output is the input and the inputs aren't bounded, so the outputs aren't bounded. All right. So once again, I've got a function that's locally bounded but not bounded. It's not because the domain isn't closed, the domain is closed. Here it's because in some sense the domain's not bounded. All right. So the main goal of this theorem is to show that those two phenomena are essentially responsible for examples like this. What do I mean by that? Here it's stated more precisely that if you take a function that's locally bounded at each point of a domain that is both closed and bounded, then your function is bounded on the whole set. All right. So a sufficient condition for locally bounded to imply bounded is the domain be closed and bounded. All right. So just kind of going over our examples again, 0, 1 is a bounded set, but it's not closed. So it's missing one of the two crucial ingredients. The interval from 0 to infinity, including 0, is closed, but it's not bounded. It's missing the other crucial ingredient. So if you have a set, this theorem is saying if you have a set that's not missing either one of those crucial ingredients, then a locally bounded function will always be bounded. Nice. Here's how we're going to get at that. I'm going to prove something called the Bolzano-Weierstrass property. We already have a theorem in this class, the Bolzano-Weierstrass theorem. I think it's theorem 2.40 in your text back in chapter 2. You might want to go back and look at it. You might want to stop the video and go back and look at it here. Because here I'm calling something the Bolzano-Weierstrass property. It's very similar. What is the Bolzano-Weierstrass property? Before I even kind of highlight this theorem, this is what the property is. The Bolzano-Weierstrass property is a property that a set might have. And the property is the following. If every sequence of points that you choose from the set has a subsequence that converges to a point that belongs to that set, and I'm going to kind of double underline that because that's the sort of important part of it. So the Bolzano-Weierstrass property is that whenever you have a sequence of points in your set, if it always has to have a subsequence that converges to a point in that set, then I'll say the set has the Bolzano-Weierstrass property. And this theorem is saying that that property is equivalent to the set being closed and bounded. All right. So if you take a subset of the real numbers called E, it's both closed and bounded if and only if it has the Bolzano-Weierstrass property. I'm just going to kind of summarize that. So E is closed and bounded if and only if E has the Bolzano-Weierstrass property. That's what our theorem is saying. All right, so I want to give you a proof of it. It's a double implication proof. So we'll prove each implication one at a time. All right, so let's start off by assuming that I've got a subset that's both closed and bounded. And then if I want to show that it has that Bolzano-Weierstrass property, I should choose some sequence, any sequence that every single term of it is in E. All right, so that's how we're going to start. Assume you have a closed bounded set, take a sequence in that set. The set's bounded, so the sequence is bounded. Okay. If the set is bounded and the sequence terms are all in the set, the sequence is bounded. So I am going to use the Bolzano-Weierstrass theorem from chapter 2. This sequence has some convergent subsequence. I'm going to call it x sub n sub k. That's what the Bolzano-Weierstrass theorem says. Every bounded sequence of real numbers has a convergent subsequence. And I'm going to name its limit. Let's call its limit x. So x sub n sub k converges to x as k goes to infinity. Our goal is to show that x is an E. All right. I'm going to kind of handle this by cases. It's not likely, quote unquote, but it's not impossible that this subsequence is just eventually constant. So what would I mean by that? I mean, there's some value of the index that beyond it, the sequence terms never change. Xnk is xn sub capital N for all k greater than or equal to n. Well, if that's the case, then the limit x has to be that constant value. The sequence terms are in E, so x is in E. All right, so if the sequence is eventually constant, then kind of trivially we're done. If the sequence is not eventually constant, because the subsequence, if it converges to x, then given an epsilon, I can find some capital N that the subsequence terms are in the epsilon neighborhood of x eventually. That is for k greater than or equal to capital N. Yeah, again, those subsequence terms are all in the set E. All right, so what does that mean? That means that this epsilon neighborhood of X intersect the set E is infinite. It contains all of these subsequent terms, and there's infinitely many of them. Epsilon was an arbitrary number. So that means by definition, X is an accumulation point for E, right? An accumulation point for E is a point for which every epsilon neighborhood intersects E in infinitely many points. So we've shown that this X is such a point, but E is a closed set. Closed sets contain all their accumulation points. So to summarize the argument, if this set is closed and bounded, then our arbitrary sequence in it has a subsequence that converges to a point that's in it. Okay, that is, the set has the Bolzano-Weierstrass property. Nice. Turning it around, now we're going to suppose that we have some subset E that has the Bolzano-Weierstrass property. That is, suppose that every sequence in E has a subsequence that converges to a point in E. Right, so it's a stronger assumption than just saying it has a convergent subsequence. The limit of this convergent subsequence has to belong to E. And I'm going to show you that E is closed and bounded, and I'm going to do it one at a time, bounded first, and both are going to be sort of by contradiction. You could probably rewrite them as contrapositives. So I'm assuming what I've highlighted in yellow, and then suppose for a contradiction that E is not bounded. Okay, so if E isn't bounded, that means its terms, there are elements of it rather, that are arbitrarily large. In the following sense, if you give me any natural number, I can find an element of E. I'm going to call it X sub n because it depends on the natural number, and X sub n is bigger than n. All right, because why? Because that natural number n cannot be an upper bound for E. There has to be something bigger than it in E. So doing this for each natural number, we generate a sequence. I'll call that sequence X sub n, and it's a sequence in E by definition, by construction. Every one of its elements, terms, is an element of E. All right, and then I'm going to leave it to you to check the details, but by construction, again, that sequence converges to infinity, or excuse me, it diverges to infinity. The nth term is bigger than n, so it's diverging to infinity. So if you take any subsequence of it, any subsequence of that sequence is also going to diverge to infinity. Again, you can check the details. So in particular, that subsequence cannot converge to a point of E, but that's a contradiction. We said we were assuming that every sequence in E has a subsequence that converges to a point in E. So why did we get a contradiction? We got a contradiction because we assumed that E wasn't bounded. So it follows that E has to be bounded. Cool. All right, now I want to show you that E is closed, and I'm also going to use the same kind of logical structure. Suppose E is not closed. Okay, suppose E is not closed. Actually, sorry, I'm going to give this one directly. I'm going to argue that any accumulation point has to be an element of E. So let's pick an accumulation point of E, call it X. All right, this is going to be, it's sort of, I think, already starting to feel like a familiar construction. If you have an accumulation point, it means every epsilon neighborhood has infinitely many points in it, or every deleted epsilon neighborhood has a point other than X that's also an E. So in particular, if I take epsilon to be 1 over n, for any natural number, n, 1 over n is a positive number, I have to be able to find some point in E, call it X sub n, that's not X, it's in the deleted 1 over n neighborhood, okay? And it's in there. That's because X is an accumulation point. So you can check the details, but that sequence defined by these X sub n's converges to X. Why? Because given an epsilon, I can always choose 1 over n less than, choose n so that 1 over n is less than epsilon, and it will stay that way. So check it, but that's sequence constructed converges to X. Okay. Now I'm assuming that this set E has the Bolzano-Weierstrass property. I've got a sequence in E. Every sequence in E has a subsequence that converges to a point in E. I'm going to call the limit of the subsequence Y. But that's just temporary, because if the sequence itself converges to x, every subsequence has to converge to the same limit. We proved it in the subsequence section. So this x and y are really the same, and y belongs to E, so does x. So E contains all of its accumulation points, so it's a closed set. All right. This corollary just kind of restates the theorem in terms of accumulation points. That it's really not something new. It just it kind of follows from the argument that we gave, that a set is closed and bounded if and only if every infinite subset has an that has an accumulation point belongs to E. All right, so that infinite subset, you can select the sequence like what we did before. I'll let you check that out. Okay, so with this Bolzano-Weierstrass property, or rather its equivalence to the set being closed and bounded, we can prove the main theorem of this lecture. The main theorem of the lecture is that if you have a function that is locally bounded at every point of a closed and bounded set, then it's bounded on that set. Okay, so if the domain is closed and bounded, locally bounded implies bounded. Let's do it. We're going to give the proof. We're going to use the Bolzano-Weierstrass property that we just proved. So let's take our subset E and suppose it's closed and bounded, and then take some function on E that's locally bounded. So that's just setting up the hypothesis. And then I want to show that F is globally bounded. I want to show F is bounded. So I'm going to go by contradiction. Suppose for a contradiction that F isn't bounded. All right. And then what am I going to end up contradicting? I'm going to kind of contradict the Bolzano-Weierstrass property, or rather a sort of a consequence of it. Okay, so if my function isn't bounded, then for every natural number, I should be able to find some domain element, I'm calling it x sub n because it depends on the natural number, whose absolute value of the function value is bigger than n. That's because no natural number is an upper bound for this function's range. The function is unbounded. All right, so that generates a sequence, x sub n in E, and the Bolzano-Weierstrass property says that that sequence has some convergent subsequence, and it converges to a point in E. All right, but now my function is locally bounded on E. It's part of the hypothesis. F is locally bounded on E. X is in E, so there has to be a couple of numbers, epsilon x and mx, so that for every y in the epsilon neighborhood of x, F is bounded by mx. Okay, so that's true on this entire neighborhood. But our subsequence converges to x. So its terms are eventually in this epsilon sub x neighborhood. That is, there's some number n, so that if you take k larger than n, then your subsequence terms are in that epsilon neighborhood. So in this epsilon neighborhood, F is bounded, and the subsequence terms eventually get in there and stay in there. Okay, so for k greater than or equal to n, the images of the points in this subsequence are no more than this m sub x. They're less than this m sub x. Good. Put that on ice. So remember this. I'm going to kind of underline it right here, that the subsequence terms are less than m sub x as soon as k is bigger than or equal to this number n. All right. So now I'm going to choose a natural number, little k. This is always true, that the kth subsequence index is bigger than k. Choose that bigger than this n and this m sub x. Okay, n's a natural number, m sub x is a positive number. Pick a natural number k that's bigger than both of them, and notice that n sub k is bigger than or equal to that. Okay, so by construction of the sequence, remember we set up here that when we built this sequence, f of x sub n is greater than n. So by construction, f of x sub n sub k is greater than n sub k, which is greater than mx. N sub k is bigger than or equal to k, which is bigger than mx. Okay, so that's one thing I have. Let me highlight it in green. So I'm choosing this k in such a way that I have that. But this k is also bigger than n because it's bigger than the maximum of n and m sub x. So that means that by the part that we already talked about, f of x sub n sub k is less than mx. Well, those two things that I've highlighted in green cannot simultaneously be true. F of x sub n sub k cannot simultaneously be bigger than mx and less than it. So that's our contradiction. So where did the contradiction spring from? It sprung from when we assumed f wasn't bounded on E. So therefore f is bounded on E, and that completes the proof of the theorem. All right, thanks for listening.